Hi all, thank you for joining day 5 of Wireless Foundation session. So let us start our exploration on the antenna. So in the previous session also we discussed the introduction of antenna. There are types of antennas designed for many different purposes as I explained previously. So just as there are many types of lights designed for many different purposes, when purchasing lighting for your home, it is easy to compare two lamps by turning them on and looking at the way each disperse the light. Unfortunately, it is not possible to compare antennas in the same way. Antenna gain is normally a comparison of one antenna against an isotropic antenna. And what is an isotropic antenna? We have understood in our previous session. So isotropic antenna is a ideal antenna that is going to radiate in all 360-degree direction. Okay. And antenna gain is normally a comparison of one antenna against an isotropic antenna. And this measured in the unit that is nothing but dBi. Okay. And it is impossible to construct an isotropic antenna and it does not actually exist, but it is ideal and perfect to um, compare it with the other types of antenna that we are going to learn today. When an alternating current is applied, an RF signal is generated and electromagnetic waves are radiated equally in all the direction. Okay. The energy produced by the antenna takes the form of ever expanding sphere, just like a balloon. So it is like ever expanding sphere, it will take that kind of structure. If you were to move all around an isotropic antenna at a fixed direction, suppose this is your antenna and you are moving isotropically in a fixed direction, you would find the signal strength is the same. An actual side-by-side comparison of antennas requires you to walk around the cell, okay, the cell that this antenna builds. Suppose it's an isotropic cell. You need to walk with an RF meter, take numerous signal measurements, then plot the measurements of a piece of on a piece of paper. So instead of going through such hectic tasks, antenna manufacturers create something called as azimuth chart. Okay, commonly known as radiation patterns for their antennas. These charts are commonly also known as polar charts or simply as antenna radiation envelopes or else the radiation charts. These charts are like most physical antennas are not ideal. Okay. Sorry. These physical antennas are not ideal. So their radiation pattern is not simple to understand. So we say that when the radiation goes out of the antenna, so it is like radially 360-degree direction. But there are different kinds of antennas that are present in the market. That is, one of the type is omnidirectional antennas, semi-directional antennas. The third type is highly focused antenna or highly focused antennas are there. As we know, we are not going to provide any external source like a battery source to provide the gain. It is just a passive gain where, for example, if a stream of water is flowing, okay, randomly it is flowing everywhere, but you build a kind of a checkpoint where you are streamlining that all the water that is going everywhere to a single, stream of water through some pipes. So now this becomes highly directional. Okay, and the pressure will be very high compared to here because it is randomly going and there is a lot of space. Now what happened? The same water you are having at this side also, but it is more channelized, so it is the pressure is more high here at this point of time. Similarly, the power that goes out of the antenna, it has to go in a radial fashion. So instead of going in radial fashion, you're concentrating the power at some particular space. So that is why it has a passive gain. So we are not providing any external charge there, external factor which can increase the power, but it is just a passive power. Whatever the power that was supposed to radiate in all the 360-degree direction, you're focusing at a particular space. So that is why you have a passive gain there. Okay, and the antennas are not ideally like this. I mean, the antenna radiation, so they're having some pattern. So when you are purchasing the antennas, so you should be aware of that or of those patterns, and depending on those patterns you have to purchase the antenna. So in this session we would be seeing what kind of antennas and all. So yeah. We compress the signal instead of letting it go in isotropic fashion. The total of outputting power remains the same, and only thing is we make the signal strong near to the radiator where we measure gain of antenna. Different antennas are designed for various purposes similar to different types of lighting. Antenna gain is measured in dBi, comparing an antenna to an ideal antenna. Isotropic antenna. It is a hypothetical antenna, radiates equally in all directions, forming an expanding sphere of energy. So the radiation is nothing but energy, right? So it is like ever expanding in the atmosphere. But as it goes away from the impact, from the point of impact, so it gets weakened. In the first session, we have understood when a person sticking a hand into the pond, so it is creating ripples. The ripples, when it moves away from the finger, so it becomes weaker. Okay, we can use that analogy in our antenna concept. So radiation patterns, manufacturers provide azimuth chart. Okay, in that azimuth, H plane and elevation is E plane charts, also known as polar charts. So we'll be looking at those charts in a bit now. Azimuth and elevation charts. Top-down view of the antenna radiation pattern. The outer ring represents the strongest signal, similar to the shadow cast by a flashlight. The shape of the radiation pattern remains consistent regardless of the power changes. The plane at the right is known as E plane, that is here. Okay, and this side it is called as H plane. Okay, and H plane, E plane or elevation plane, and shows a side view of the radiation pattern. So the E plane basically shows the side view. H plane, that is horizontal, you look it when you are looking from above. Suppose you are standing here. So if you are looking from above, that is the H plane. If you are looking from the side, okay, that is E plane. This is H plane. When you're looking from above, sorry, from here. When you're looking from here, that is the H plane. When you're looking from the side, it is the H plane. So these are the two planes that are present in the chart. So as you can see here, so this is the H plane when you're looking from above. This is the E plane when you're looking from the side, that is this one. This one, okay, like this here. When you're looking from above, it is like this, from the above. This will be more clear in this picture. You can see this is the H plane, horizontal like this. When you're looking from here, vertical, it will be like this. That is here, sir. Here. All right, this is the H plane. This is the E plane. You can see the rings over here. This is the antenna, and the inner circle is minus 30 dB, and minus 25, minus 10, minus 15, minus 10, minus 5, 0 dB. Okay, so like this, it starts from 0 dB. This is the ideal ring, but it will not be like this. In the next slides, you will come to know how will be the radiation pattern. But as you can see, if the antenna is here, it is minus 30 and it is minus 5. So minus 30 is a better signal or minus 5 is a better signal? So which one is a better signal? So minus 5 is a better signal, right? So if the minus 5 is a better signal, that means what? So normally in the polar charts, the antenna is placed at the center. Okay, the antenna is placed at the center, suppose here, right? So the antenna is placed at the center. This is not a good diagram, but so suppose if antenna is here, so it is going to radially, it is going to go in all the 360-degree direction. Okay. And now the antenna is placed in between in the polar charts. And you know that if the antenna is here, the nearest, if if the person is sitting at this point, so he is having highest signal strength, so it will should be minus 5. If he goes little bit far, so maybe his signal strength is like minus 20 dB. Here he is minus 5 dB. But here in this chart, here it is lesser signal strength, while is going away from the chart, I mean going little bit far away from the chart, it is like minus 5, which the signal strength is high. So how to understand this? So the analogy is, when you look at this chart, what is this telling? It is a H plane. This one is a E plane when you're looking from the side. But the way that you need to look at is, if you have like this, see this is one ring, this is another ring, this is another ring like this. And you have a point like this. I think this is not a good picture. Okay, so what we are trying to understand in this session? So in this session, we are trying to understand the antenna part. Okay. So in that process, we are learning what is a H plane, what is a E plane. H plane is a horizontal plane, as you can see in this diagram. Okay. E plane is a vertical plane, that is when you are standing here, if you are looking from the side, so how the radiation looks. So that's what the H plane is. So now we had a question. If an antenna is placed in between in the polar charts, why the nearest value is minus 30, right? It is looking like that. It is minus 30, where the farthest value is minus 5. But we know from the previous sessions that when the antenna, the signal near to the antenna has a higher signal strength, but as he moves away from the antenna, the signal strength gets degraded. But in this chart, how is it possible that the nearest signal to the antenna is having the lowest power, whereas the distance is increasing and it is like the signal is getting stronger? So that's not possible. So what exactly it is happening here is, if you take this picture here, so take multiple rings. Okay, one ring, two ring, three ring on the top, or else like this. one ring, two ring, three, four, five, six, seven, eight, like this. So from the top like this and like this, straight line. So what happens is this minus 5, right? So that is nothing but that comes somewhere here. The antenna is here. The second ring is here. The third is here. The fourth is here. But when you look from above, right? So this is the first point that you see. But where is the antenna? That is here. So the first one that you are seeing, that actually is here. Okay, that is why it is minus 30. So the next one that you see, that is here, that is minus 25. The other one that you see, that is minus 20, minus 15, minus 10, and then minus 5. So like that you need to analyze it. Okay. That is the farthest. When you look from above, right? So it looks like it is near. It is near to this. But when you're looking from above, obviously it is like minus 30 is the farthest point from that antenna. Can't see your drawing. Can you see now? This one. Okay. You want me to erase and yeah, yeah, sure. See, when you're looking from above, H is what? From the top view. When you're looking from above, so you make this as one ring. This is the another ring. This is one more ring. Again, there is a ring here, ring here. And there is a, oh, sorry. And there is a ring here. Okay. And there's a ring here. So now at the top. So it is going like this. And here it is like this. Okay. So this is the first ring. The antenna is placed somewhere here. Okay, the antenna is placed here. So the first ring you are seeing, that is nothing but minus 5. That is this one. Okay, minus 5. Then it is like minus 10. When it is going up, 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 the last one is, that is minus 30. When you're looking from above, the nearest one is the one that you see first. Next is minus 25. That is here. Minus 20, minus 5, minus 15, minus 10, minus 5. So the one that is at the focal point, so that is what the minus 5 is. So that is how you look, you have to analyze. When you're looking from above, right? When you're looking from above, so minus 30 comes here somewhere. So that is far from the antenna. Minus 25 is this one, minus 20, minus 15, minus 10, minus 5. So when you are looking from above, this one is the nearest one. So that's why it is showing like this. Okay. So you might get confused when you look at this diagram. If I say in a polar chart, the antennas are placed in the middle, and if it is in the middle, it is the nearest point. So it is minus 30 is a poor signal compared to minus 5. Okay, how come it is not near? That is because when we look at it, it should be in a 360-degree direct, 360-degree. So when you look from the top, so minus 30 is the first that you look, then minus 25, minus 20, minus 15, minus 10, and then minus 5. But actually the minus 5 is closest to the focal point. So that is why it is having the high strength. Okay, that is how you need to look at this azimuth chart. Is it clear? Is it confusing? Do you want me to repeat? Okay, I will take that as a yes and I will move on. So gain, antenna gain. I have already told you it's a passive gain. Antennas are passive devices. They do not amplify a transmitter signal with any circuitry or external power. The gain of an antenna is a measure of how effectively it can focus RF energy in a certain direction. When an isotropic antenna is compared with itself, the result is a gain of 10 log 1. So not let's just not go with that. So 0 dBi. Okay, the perfect isotropic antenna is 0 dBi. Means what? So when you have a perfect isotropic antenna, the energy is radiating in all the direction. So there is no gain, but the same energy you take and you focus at a point, so then all that energy is focused, so there will be some gain. Suppose 2 dBi is the gain. So this is a isotropic antenna that has no gain, but it is ideal. Okay, it is not practically possible to have an isotropic antenna, but when you have an antenna and you are focusing it, so then instead of indicating with a 0 dBi, now that energy which was supposed to go in all 360-degree direction, it is getting focused. So by that phenomena, you are going to get some increase in power. Okay, it is similar to a flashlight. When you have a bulb, like you have a bulb and that bulb is radiating everywhere, right? But you take a flashlight, so it is focused at a point, right? If you take a flashlight, it will focus at a point. If you change the lens, very good lens, so then it will concentrating at a single point. The energy that it is focusing is high at this point. Now in this example, the radiation is going everywhere, but here the light is getting focused on a particular place. So all that energy that was going everywhere, so now it is focused. So there is a passive gain. So that's what happens in the antenna also. No, no, it is a theory concept. Anytime isotropic antenna is not there. The gain of an antenna is a measure of how effectively it can focus RF energy in a certain direction. The gain itself is not indicated on either E or H plane. The only way to find an antenna's gain is to look at the manufacturer's specifications. There is a concept of beam width. Beam width is nothing but the focus. Beam width is the measurement of how broad or narrow the focus of an antenna is and is measured both horizontally and vertically. It is the measurement from the center or strongest point of the antenna signal to each of the points along the horizontal and vertical axis. So in the first picture, you can see this is the beam width of this particular signal that is coming out of this antenna. This is the beam width. So this beam width is high, right? The focus is high, very narrow beam width. This is the medium size. This is a short distance or the low gain wide beam width, the third one. You can see this is the isotropic antenna radiation that it can emit like this in 360-degree direction, and it is 0 dBi. So the same thing when you have a omnidirectional antenna that has a pattern like this, like a donut shape. Okay, just like a balloon, if you take and you squeeze in between, so that is the shape that it is going to take of the omnidirectional antenna, and it is having a gain of plus 4 dBi. When you use an isotropic antenna, 0 dBi, omnidirectional, it is 4 dBi. Highly directional antenna, you can see it can give an increase of gain of plus 12 dBi. Okay, plus 12 dBi. So you can see like this. Okay, when you squeeze more, so it becomes like this. There is a concept of polarization. Okay, polarization. I hope you got the concept of gain, right? Passive gain. So the beam width we have understood, like it is the focus that we are going to achieve. Okay, that's the beam width. I have told you like the flashlight have adjustable lenses, right? Enabling the user to have a tightened the concentration of light. And RF antennas are capable of focusing the power that is radiating from them in all the direction, unlike the flashlights. Okay. And antennas are not adjustable. Once the outdoor antennas specifically, once you adjust and keep them, so it will be like that only. Okay, and if you see the flashlights, there will be a setting for more focus, less focus. So those kind of things, it is not possible in the outdoor antennas. And the user must decide how much focus is desired, and the receiver's signal strength indicator, all those things has to calculated, and accordingly it has to be kept. And also few other factors like the polarization and the orientation of the antenna is important. That is what we will see in the next slide. This dBi, 4 dBi and 12 dBi is fixed or it varies. Yes, it is fixed for that omnidirectional antennas, but it depends on the manufacturer. Okay, the kind of materials that they use and all. Polarization. When an alternating current is applied to an antenna, an electromagnetic wave is produced. The electrical portion of the wave will always leave the antenna in a certain orientation. For example, most Cisco antennas produce a wave that oscillates up and down in a vertical direction. As it travels through free space, antennas might be designed to produce waves that oscillate back and forth horizontally. Still others might produce waves that actually twist in a three-dimensional spiral motion. The wave's orientation is called as antenna polarization. So the orientation is very important. You have an outdoor antenna and you are sending, the signal is oriented like this when you are sending. But the antenna that you are using on the receiver side has a horizontal polarized, horizontally polarized, but you are sending vertically polarized signal. So then that will not work. Okay. And the way it is focusing or receiving, so that also will matter. The antenna polarization at the transmitter must be matched to the polarization at the receiver. If the polarization is mismatched, the receiver signal can be severely degraded. So this is a vertically polarized signal up and down like this. And this is the sideways, horizontally polarized like this. So when you are sending the radiation, you can polarize it accordingly. Just remember the first session where you put a finger into a pond and then it creates some ripples, right? It is horizontally or vertically it will create. And the receiver side also, it should be, the antenna should be very oriented properly. That is about the polarization, and most access points use low gain omnidirectional antennas. Okay, omnidirectional antennas, which should be mounted from the ceiling. Omnidirectional antenna, just like a street light, where a street light will be placed like this and it will be focusing in omnidirection, right? Similarly, most of the corporate offices will use the omnidirectional antennas. Okay, they have low gain omnidirectional antennas, which should be mounted on the ceiling with they are vertically polarized. Okay, they are vertically polarized. Let's see the antenna types now. There are three main categories of antennas: omnidirectional, semi-directional, highly directional. Omnidirectional antennas radiate RF in a fashion similar to the way a table or a floor lamp radiates, which I explained previously. They are designed to provide general coverage horizontally in all directions. Semi-directional antennas radiate RF in a fashion similar to the way a wall radiates light away from the wall, or the way street lamp, which I gave example just now, light down on a street or a parking lot, providing a directional light across a large area. Highly directional, Antennas radiate RF in a fashion similar to the way a spotlight focuses light on a flag or a sign. Basically, a flashlight, you can take example of that. Okay. Antennas are usually designed for a specific frequency range and are approved by the legal regulatory bodies such as FCC. Okay, I will show you like the Wi-Fi Alliance, FCC. So these all things has to be registered. The devices, the manufacturer, the vendors will register the device types. Okay, that we will see the in the regulation chapter. Okay. Antennas come in various types: omnidirectional, patch antenna, Yagi antenna, dish antenna, sector, and grid, each with specific patterns and gains measured in decibel isotropic (dBi). Higher gain antennas focus the signal more narrowly, increasing distance but decreasing beam width. Okay. Highly directional antennas focus the signal more narrowly, increasing the distance but decreasing the beam width, requiring precise alignment. So when you focus more and more, the receiver antenna's alignment is very important. If it is an isotropic antenna, then you no need to bother about the receiver's orientation or the polarization. But when you have a highly, the beam width is decreasing, beam width is very narrow beam width, highly narrow beam width you are using. So then the receiver antenna should be properly polarized or oriented according to the transmitter antenna. So for example, if you are sending a signal like this, but this one is oriented little bit like this, okay, but now if they are not getting into the aperture angle, so there is some aperture angle, so within that if they are getting 60 to 70% of the radiation on that aperture angle, then it will be able to understand ones and zeros. If it is not able to hit that particular aperture point, so then the signal will be lost, maybe less than 50%, it is not able to understand. Let's see omnidirectional antennas. Omnidirectional antennas radiate an RF signal in all directions. The small rubber coated dipole antenna, often referred to as a rubber duck antenna. Earlier, these antennas, the outdoor antennas, were made up of rubber. So nowadays they are made up of plastic, but rubber was a better element to have. Omnidirectional antennas are typically used in point to multi-point environments. That is nothing but our Wi-Fi communication. You can use it. So normally nowadays in Cisco's ReLM, so we are using the antennas that are inside the AP itself. We are not using any external antennas. There are internal antennas and external antennas. If you want to provide more coverage, then you need to have external antennas. But as a wireless engineer, you should know all these concepts and nuances of these topics, because you will purchase an antenna and you will mount it, and you purchase like 4 antennas you mount it, but your clients are not upgraded. Your clients are operating at less power values, whereas your antennas are sending the signal far away, but the clients are not able to respond back. The antennas or the AP is able to reach the client, but the client is not able to reach the AP. So that those kind of situations should not happen. So that you need to properly do a survey, proactive survey. So uh, uh, then you need to purchase the antennas. High gain omnidirectional antennas can also be used outdoors to connect multiple buildings together in a point to multi-point configurations. Dipoles usually have a gain of around +2 to +5 dBi. Okay, dipole. There is full wave antennas, but normally in Cisco they use dipole antennas and monopole antenna as well. Types includes dipole antennas designed to provide a near spherical coverage pattern and donut shaped. So dipole antenna, the radiation pattern is like a donut shape, which we explained, omnidirectional antenna, with a small dead zone directly beneath it. So this is kind of a blackout area for them where the signal strength is less. Dipole antenna length should be equal to half the wavelength of transmission. Suppose you take a 2.4 gigahertz band. So in wireless communication, so we have 2.4 gigahertz, 5 gigahertz, 6 gigahertz. If you take 2.4 gigahertz, the wavelength is approximately equal to 4 inches, suppose. So the antenna length should be 2 inches. Okay, that is half the wavelength. And 5 gigahertz has a wavelength. Wavelength is what? Distance between two crust and two trough. Two crust or two trough, right? This is the wavelength. So wavelength is of 2.4 gigahertz is 4 inches. So if it is approximate, not exactly, it is approximately 4 inches. So half the value is the length of the antenna, that is 2 inches. If you take 5 gigahertz band, so the 2 inches is the wavelength and the height of the antenna should be like 1 inch. See how small it is, right? And monopole, it is even more smaller. Higher the gain we experience at the access point, this means we are really forcing the signal out in a particular direction. Distance will increase, but beam width will decrease. Okay, distance will increase, but the beam width will decrease. So as you focus more and more on a particular direction, so the beam width, whatever was there, right, it shrink to this much. So earlier it was catering more, but now it is focusing in a single direction. We need to pay special attention not only to type of antenna, but rating, coverage pattern, etc. So this is the omnidirectional antenna connectors that you can use. Okay. So these are called as TNC connectors. This is the kind of connector that you will use. So when this AC signal is generated by the transmitter and passes through the cable also has attenuation. And this is the connector. Okay, just like in the older times, you will be having this dish TV, right? So in that dish TV, you will have some connectors like this. So this connector also will lead to the attenuation, maybe of 1 dB, minus 1 dB or something like that. That is RP TNC connector, RP SMA connector, and there is a DART connector like this. So these are the antenna connectors. There is one more type of connector is that is called as DART connector. BNC is there, N type, RP type. So this is the DART connector. This is a collection of antennas. It's a single casing. It is a single casing that it will have for multiple antenna and a single cable to the AP. The DART will reduce the cabling mess created by numerous individual connections. Key consideration for antenna selection include 2.4 GHz, 5 GHz, 6 GHz, and the antenna type. Dual band antennas are convenient but less effective than single band antennas. So what is a single band and a dual band? So this is a band, okay, 2.4 GHz and 5 GHz. The wireless devices operate in this frequency range, either in 2.4 or 5 GHz or 6 GHz. So a single antenna supporting both 2.4 GHz and 5 GHz, it is called dual band antenna. Okay. And they are convenient but less effective than a single band antenna designed for a specific frequency. Antennas should match the deployment frequency to perform optimally. You can see this is the DART antenna where it has a collection of antennas. It is for 2.4 gigahertz here. And these are the cables that are being used. Okay, LMR cable. We are using coaxial cable, just like a dish TV. It will be having a shield. Okay, outside there will be a shield that will be present, thick shield. So there will be inner shield and then there will be a copper cable. Okay, these are the coaxial cables that will be used. Two connector goes to antennas of dipole, applying AC between the two different poles and will cancel out electromagnetic interference. So this much shielding is done to cancel the electromagnetic interference. Suppose the AC signal is passing through this copper wire and you bring a mobile phone near to this, then there will be some electromagnetic interferences that will happen, right? Because of the electronic device. So to avoid that, there will be thicker shield outside this copper wire. Okay, you can see here copper wires, in that there is a one shield, then there is a thick shield outside that. Yeah, this one is a clear picture here. Okay, and these cables will have the attenuation. So transmitter is going to generate the AC signal and it is going to send on the copper wire. So now that copper wire will have the attenuation. But this particular cable that you are using can support up to 30 megahertz. 30 megahertz signal it will support. And that 30 megahertz signal, suppose for every 100 feet, it will have a zero point 0.7 dB of loss it will have. If it is at 50 megahertz frequency, it will have a loss of 0.9 dB. 150 megahertz frequency, that is having 1.5 dB of loss. So when I say the frequency is 150 megahertz, so what does it mean? Can anyone answer in like a single line? It is like the signal in this copper wire, the AC signal is generated and it is traveling. So now 150 megahertz signal means what? 150 megahertz signal is passing through this cable. So what does that mean? That means 1 hertz means what? 1 hertz is 1 cycle per second. So per 1 second, how many cycles it is happening here? 50 megahertz or 50 megahertz, right? So it is like if you are transmitting a signal of 2.4 gigahertz, that is our wireless signal. So how many 2.4 billion, right? Cycles per second. So those many cycles you are going to send per second. That particular cable is capable of sending those many cycles per second. Then you will have a attenuation of 1.9 dB, 2.7 dB, 3.9 dB. Okay. So that is what it means, this chart. Okay. So that is what this chart is. Yeah. You can see 1 by 8, 3 by 6, right? This is the wavelength calculation. I hope you got this concept. Is it boring? Like, are you feeling bored? I hope you're not getting bored with these concepts. Okay. So now we have the omnidirectional antennas pattern. So I am almost close to the concept that I am going to talk about, which is important here. So omnidirectional antennas, you can see vertical direct radiation patterns of omnidirectional antennas. If you look, vertical means what? Vertical is nothing but the H plane, right? Sorry, E plane. That when you're looking from the sideways, that is vertically. When you're looking from the sideways, the radiation patterns look like this. Suppose if a person sitting here, the signal is blacked out here. Okay, this is the radiation pattern. Suppose this is a radiation 1, I will say. This is a radiation 2. This is my antenna. Okay. So now answer my question. If I want to go from 1 to 2, what factor I need to increase? What factor can make the radiation from 1 to 2? What factor I need to tune? Power. Yeah, that's the right answer. So when you increase the power, so you can focus. That is one correct answer. The second answer is you need to use that particular antenna. Okay, whether you are using omnidirectional, isotropic, so that also will matter. It is not only the power. Power is like how much distance it can go, how much distance it can travel. But when you, the shape of the antenna, the orientation, the polarization, so that's what makes the lobe to look like this. This is one lobe. Okay, this is called as one lobe. See, these are the lobes. So when you have these antennas and you are sending the radiation, it is not exactly like this, but somewhere it will be like this, like this, like this, like this. There will be multiple lobes around it, but this will be the proper lobe it will be having. It is like practically it will be like this. Okay, when you increase the power, obviously it is going to focus more, but power is related to how much distance it can travel. But the shape of the antenna, the polarization, the orientation, so that defines how whether it is a omnidirectional, whether it is a highly directional, or it is an isotropic antenna. Okay. So if you see here, the prominent line, this is having a 2.14 dBi of gain. The second lobe that is there, this one, it is having 5 dBi. The inner one, it is having 9 dBi gain. So this is the working of a high wave dipole antenna. If you have your home Wi-Fi, you might be having two antennas like this. So it is made up of plastic. So if you peel that antenna, it will look like this. Okay, it will have two wires and a high half dipole antenna. We know that it is an open circuit. Okay, the charges will move up and down, up and down, up and down, and it will create the radiation like this. Okay, half dipole antenna. Dipoles are often connected to a wireless LAN devices that mount on the ceiling of a room and hallways. Most dipole antennas are between 3.5 to 5.5 inches long. So you can see this is the Cisco dipole antenna, and you can see the polarization that it is having. This is vertically polarized like this. This is a horizontally polarized like this. To reduce the size of the omnidirectional antenna even further, many Cisco APs have integrated antennas that are hidden inside the device's smooth cases. Integrated omnidirectional antennas typically have a gain of 2 dBi in the 2.4 gigahertz and 5 dBi in the 5 gigahertz band. Okay, this is the omnidirectional antenna gain for 2 gigahertz band and 5 gigahertz band, that is 2 dBi to 5 dBi. So just remember the values. So this is the actual picture, okay, radiation picture. If you take a omnidirectional antenna, okay, we studied it will be a ring, but it will not be a ring. It will be actually like this, okay. So ideally, isotropic antenna is like this, but in practically, if you purchase a omnidirectional antenna, it will be like this, okay. This is one example, E plane, H plane, and this is a donut shape. This is a monopole antenna. Okay, Cisco monopole antenna, small antenna. You can see this one, integrated omnidirectional antenna, and this is one of the antennas azimuth chart. Okay, when you look from the side, it looks like this, radiation. When you look from the top, it looks like this. Unlike omnidirectional antennas, which radiate an RF signal in all directions, so this we have studied. Types include planar antennas. So semi-directional antenna are used for short to medium distance communication, with the long distance communication being served by highly directional antennas. Patch and panel antennas, more accurately classified or referred to as planar antennas, includes planar antennas such as patch antennas, Yagi antennas, patch antennas. Patch and panel antennas provide focused coverage in a specific direction, often used in hallways or cover specific areas. These antennas can be used for outdoor point-to-point communication, that is, one antenna communication to another antenna communication. But in our offices, we are going to use omnidirectional antennas, or sorry, semi-directional antennas, that is focusing in a single direction, that is point to multi-point, like multiple users. And in the semi-directional antennas, we have patch antenna, panel antenna. They are specifically called as planar antennas. And then we have Yagi antenna. Okay, that is also one type of antenna. Before the advent of 802.11 MIMO radios, patch and panel antennas were used in indoor with the legacy .11 ABG radios. Yagi antennas, more directional than planar, often used for short point-to-point links or TV antennas. Another benefit of semi-directional antennas is that they can be installed high on a wall and tilted downwards toward the area to be covered. So the one that we use in our offices. Semi-directional antennas, you can see here the exterior of patch antenna and internal antenna. and this is the Yagi antenna, you can see like this. Okay, this might you might be seen. Yes, we will use both like semi-directional and omnidirectional depending on the usage. I will show you that pattern how it is in the next slide. Semi and omnidirectional. Yagi antenna are commonly used, just Yagi antenna. They are typically used for short to medium distance point to point communication. These are all outdoor antennas. Okay. Then parabolic dish antenna, you might be knowing that the dish like this, the older dish antennas are there. Okay. Highly directional antennas are used strictly to point communication. There are two types of highly directional antennas: parabolic dish antennas and grid antennas. The parabolic dish antenna is similar in appearance to the small digital satellite TV antennas. Okay, you might have seen in many places this parabolic dish antenna. Grid antennas, it is kind of a grill of barbecue with the edges slightly curved, and there will be space. The spacing of wires on a grid antenna is determined by the wavelength. Okay, and here you can check out. So this is the grid antenna. Okay, this is how the grid antenna. There is a space in between. And dish antenna, it is highly directional. You can see if it is a directional antenna, right? So you can see the radiation in a single direction, but practically it will not be focused like this, like a exact beam width like this, but it will be like this, and there will be a smaller lobes in the other direction as well. Okay, here also signal will be there, but they are weaker signals. Here you can see highly directional antenna. Smaller lobe is there, but on the other side, you have the complete radiation pattern like this. And why it is 20, 15, 10, minus 5, sorry, minus 20, minus 15, and this one I have explained. Sector antennas are also one type of antenna. They will provide a cover of full 360-degree area, commonly used on cell tower. Basically, it is like a cell tower, right? So you might have seen in the outside world, like it is a cell tower. Sector antennas are a special type of high gain semi-directional antennas that provide a pie-shaped coverage pattern. These antennas are typically installed in the middle of the area where RF coverage is desired. Sector antennas can be mounted high over the terrain and tilted slightly downwards, with the tilt of each antenna at an angle appropriate to the terrain it is covering. So then antenna accessories, we have learned about the cables, connectors, then we have the amplifiers. Okay, different connectors we have studied, the BNC, N-type connector, cables, coaxial cables, LMR cables we are using for outdoor purposes. This is just for your information. As a wireless engineer, you should know. But in our day-to-day corporate offices, we don't use that because it is not outside antenna. But as a wireless engineer, if you have a knowledge of this, it's always a plus. Then we have attenuators, okay, which is used to lower the energy, right, at the receiver side mostly. Lightning arresters, grounding rods and wires. You can use lightning arresters. It is used to protect the transmitter, which is more costlier, right? So you have the antenna cables, attenuators, and amplifiers, and then you are having the antenna. And if a lightning gets struck to this antenna, so the lightning arrestor will have a grounding which will lower that impact, and it will ground that particular thing that is coming. So it will not let the transmitter to spoil, but the lightning arrestor will get spoiled. You need to replace it. So instead of replacing a transmitter itself, which is very costly, you will just use this one. Okay, that is the use of lightning arresters. And also you will have grounding rods and wires and all for protecting your infrastructure. And then you have visual line of sight and Fresnel zone. Okay, so this one we will check out in the next session, and also SNR, which is a very important concept. So we'll check out in the next session. So what is a SNR? What is a visual line of sight? And also MIMO. In the next session, we will learn MIMO, multiple input and multiple output. And I think before going to MIMO, we will learn about the bands. Okay, bands we will learn in the next session. So then we will go for the MIMO concept. So next session, we will learn about that Fresnel zone, SNRs, channels and bands that we have in the wireless communication. And then if time permits, we will learn about the MIMO as well in tomorrow's session. In outdoors, normally in cell towers and all, highly directional antennas, as we talked about, sector antennas. Okay. And in indoor, omnidirectional and semi-directional antennas we will use. Tomorrow I will show you that data sheet of the antenna that Cisco uses. So you will be more clear on that. I thought of showing it today, but time is up. So tomorrow I will start with that where I will show you the data sheet of one of the antennas. Okay, and then we'll start from there. So this week we will be covering the theory part. So next week, hopefully, we'll start the WLC and AP. It will be more interesting for you. I hope this session made sense to you in terms of antennas, what are antennas, to understand the antennas. Tomorrow, when we look at the data sheet, again, you will see these coverage patterns. Okay. You will understand what these semi-directional antennas and all, and how to purchase the antenna. Okay, depending on your requirement, so that you will be more clear on that.